In this video, we're going to discuss average rate of change. Before you start watching this video, make sure that you watch the Module 4 Introduction to Average Rate of Change, Average Speed video. The video that I discussed two toy cars as an example. Okay. So, learning objective of this section are understand the covariant relations between two quantities, which is just rate of change. Understand the average rate of change in terms of relationship between two quantities. And be able to compute AROC, which is short for average rate of change, using difference quotient. So before we talk about average rate of change, let's discuss what is a rate of change. Rate of change describes how an output quantity, which is known as dependent variable, changes relative to the change in the input quantity. So the units on a rate of change are output units per input units. So examples of rate of change. Velocity, as we saw in that introduction video, speed of a car. Velocity relates two quantities, distance and time. Gas mileage also relates distance and amount of gas. Miles per gallon, right? Mile is a unit for a distance, and gallon is amount of gas. Another example, population change, which relates two quantities, number of people and time. And there are a lot more examples of rate of change. Okay. So rate of change is this concept that relates two quantities and how two quantities change in relation to each other. So how do you represent changing quantities? Let's look at this example. Frank started to eat healthier and exercise. As a result, his weight went from 195 pounds to 175 pounds. What was the change in Frank's weight? So change in weight, this triangle symbol is called delta. So let's W is weight. So delta weight represents change in weight. Is we find a change between these two weights. 195 minus 173. So 22 pounds. So we use delta, this symbol, next to the symbol of a quantity to represent change in quantity. Okay. So delta represents change in certain quantity. So theta x means change in quantity x. So let's look at another example. For x1, x of 1 equals 3 seconds and x of 2, 7 seconds, we can represent delta of x as change. How much has it changed between these 2 points? x2 minus x1 gives me 7 minus 3, 4 seconds. And if the number is positive, that means that we have positive change or increased change. If it is negative, we have decreased change. Okay. So, before we look at exact definition of average rate of change, let's just try to make sense out of average rate of change using an example. The population N of United States depends on the date D. That is, N equals N of D. That means the capital N is a function as an input quantity, date as input quantity, and output is N of D. Is a function of D. And this function is given in table. So first identify the dependent and independent variable. Okay. So here, dependent variable is population. The independent variable is time, date, years. Okay. So the population depends on years. Okay, time is independent here. Okay. So what was the increase in population from 1970 to 1980. So what we do is we look at the population in 1970, and we look at the population in 1980. Okay, then we see how population has changed. So change, delta means change in N of D, right? Equals N of 1980 minus N of 1970. So this difference shows how much it has changed between these 2 years. So we do 22723 millions minus 203.98, and we get 23.25 millions. Okay, so that's how much population has changed from 1970 to 1980. So let's try to compute the average rate of change between these two populations, 1970 and 1980. So from these 2 years, 1970 and 1980s, we had increase of population 23.25 millions over a 10-year period. Because 1970 to 1980, 10 years has passed. So we divide by 10 years. Which is equivalent to 2.325 millions per 1 year. So we're dividing by 10 essentially. We divide 23.25 by 10 and we get 2.3225 millions, which we can just write 2.325 millions per year. So this means the rate of change, we're averaging the rate of change. Okay, so sometimes we call it average of rate of change. So this 2.325 millions per year relates two quantities, population and time. And in average, we had an increase of 2.325 million of population per each year. That's how we interpret it. Okay. So it makes sense why we divide by 10, because that's how much input quantity has changed. Okay. So let's look at average rate of change as a constant rate of change. So here we're going to try to compute the average rate of change of function f of x equals 7 minus x squared over the interval from x equals -3 and x equals 5. So here is a graph of a function f of x. Recall from the introduction video of two toy cars' speed, the average rate of change of function over an interval of input values is the constant rate of change of a linear function that has the same change in output values and as the original nonlinear function over the interval of input values. So let's demonstrate that in this graph. So we're interested in computing the average rate of change of function f from -3 to +5. So then we evaluate these at these 2 points. So we'll imagine a linear function in this blue graph that for the interval from -2 to 5 has the same change in y values as the function f does. So this blue function right here, let's call it g of x. This has same change in output for the same interval, -2 to 5, compared to f of x. So the amount of change in x values is 8. This green is we do 5 minus negative 3 gives 8. Change in x, delta x is 8. Okay, so another way of saying the change in x is just delta x. Or we can also call it distance between 2 points is 8. Since the values of functions f and g are same at the endpoint of this interval, so endpoint is in negative 3 and 5 are endpoints because those are 2 points we're looking at. Okay. We can replace, so first let's actually write the change in output, which is g of 5 minus g of negative 3. Because we plug 5 for g and plug negative 3 for g. But since the values of function f and g are same at these endpoints in this interval, we can replace g of 5 and g of 3 with their corresponding values from the function f. Like this. So the constant rate of change of this linear function, this blue graph, which is a linear graph, is given by ratio of its change in y values, which is this amount of this value right here, and the corresponding change in x values, which is divided by 8. Which for this particular function, if we evaluate 5 and negative 3, so I plug 5 here and I plug negative 3 here and subtract from each other, is equal to negative 2. Okay, that means it is decreasing. So average rate of change of function f, the curve graph, over the interval from negative 3 to 5 is equal to this constant rate of change. So average rate of change is function over negative 3 to 5 equals to negative 2. So let's summarize what happened here in the next slide. So there are two observations. The function g is linear and it has constant rate of change. Again, the blue graph is linear. And this constant rate of change also can be interpreted as a slope of this linear line. And this linear line is also has a name called secant line. So this blue line, straight line between 2 points, is called secant line. Second observation, as we can see the function f and g have same average rate of change from the interval negative 3 and 5. So these two graphs, the curve graph f of x and the linear graph g of x, they have same average rate of change from the interval negative 3 and 5. So above two observation tells us that average rate of change of a function f from x equals x1 to x equals x2 is the constant rate of change of a linear function g that has the same change in output as the function f over the interval x1, x2. So same interval. So this is what it means to have average rate of change. And the way we think about average rate of change is actually constant rate of change between 2 points that is linear. Okay. So let's try to summarize. We'll kind of write some more of a formal definition. So average rate of change, the average rate of change of function from two interval points, two input quantities, is given by delta f over delta x. So change in f over change in x, which is, again, same idea of slope in linear function, right? You also might have heard the idea of rise over 1. Similar, exact same idea here. And for increment delta x, we write delta x is how much change in the bottom, and top is a plus delta x as an input minus a. A is just a point. So here are two graphs here. Okay. So again, this blue line, this straight line is called secant line. And this linear line, this function, has a constant rate of change. And this constant rate of change is the average rate of change of this curve graph between the points A and X. So finding slope of the secant line is finding the average rate of change of the function curve graph between A and X. And another way we write this function is a and a plus h. Again, a is just a point. And we denote this change in x as a h. This is very important. Although we only see h, h usually means delta x, change in input quantity. Okay. So next page, let's look at an example. For a function f of x equals x squared, we can calculate the average rate of change from x equals 3 to x equals 5 as follows. Okay. So average rate of change is delta x over delta x, delta f over delta x. So change in f, in order to find that, we plug 5 and 3 to f and find the difference between these two values, to output quantity. And for change in x, it's just 5 minus 3. Then I plug 5 here, then I get 5 squared. I plug 3 here, I get 3 squared. Then we'll get 25 minus 9 over 5 minus 3, which is 16 over 2, 8 over 1 was 8. So we found out the average rate of change of this function between 2 points, 3 and 5. So we're finding specific average rate of change value from specific interval, specifically 3 to 5. So average rate of change is 8. So delta f over delta x equals 8. So let's see how we can interpret this. Okay. So we write it delta, you can think as we multiply delta x both sides. Then we get delta f equals 8 times delta x. That means that the output quantity, function f of x, is changing 8 times as large as the input quantity, x, between x equals 3 and 5. So in this interval of input quantity of 3 and 5, the function is changing 8 times as large as the input quantity in average. So I'm going to have you the video problem. Oops. So pause the video, submit your answer in Canvas. So it'll be actually in week 6 tab, since we have changed the schedule, right? So rock dropped near the surface of the earth travels in this, according to this function, d of t equals 16 t squared feet during the first t seconds of the fall. So what is the average rate of change, or average velocity? Velocity is an example of rate of change of the from time t equals 2 to 3 seconds. So basically find the average rate of change of this function 16 t squared between these 2 points. So pause the video, write it down on your own paper, and type the answer. Only type the numerical answer in Canvas. Okay. So then let's look at how we can calculate average rate of change in general. Because what we looked at so far is how to find average rate of change between two specific input quantities or specific interval. But we want to find general expression, general function, so we can find average rate of change between any 2 points. So in general, we can find average rate of change between 2 points, x, f of x, and x plus h, f of x plus h, by computing change in f over change in x. And this expression, so let's go one by one. The top part, the numerator here, f of x plus h minus f of x, this shows change in output quantity. And input quantity is x plus h minus x. And x cancels out. That's how we have h. So this h actually represents delta x. That's the meaning of h. Changing input quantity. And so this expression is called difference quotient. I know we've seen this before, but now we're learning the meaning of difference quotient. So let's look at this. Again, this is just an example graph. We have this curve. We want to find average rate of change between point x and x plus h. Then we can imagine drawing a secant line or linear function that has same output change as the curve graph. So this height right here, a to b, is equal between this curve graph and straight graph, between this interval x and x plus h. So finding this slope is finding average rate of change between x and x plus h, which we can use difference quotient to compute. Again, I want to emphasize this again. We can think of h as a horizontal change between 2 points. Okay. So h represents change between 2 points. That's something we should remember. So let's look at this example. Compute the difference quotient of f of x. So difference quotient is because it's called difference quotient because we're finding difference in output quantity over difference in input quantity, and it's a quotient. Okay, so it's just a name, but the meaning is average rate of change. So this function is essentially find the general expression for this function that represents average rate of change. So again, average rate of change is change in output quantity over change in input quantity. F of x plus h minus x, f of x divided by h. So this is called difference quotient. And now we know meaning of this. This represents average rate of change between 2 points. But in this case, 2 points are arbitrary, x and x plus h. And h is just increment, how much has changed from x to x plus h. So here is more algebra steps. So let's go one by one. First, we need to find f of x plus h. That means I need to insert x plus h as input quantity for function f. Then I get x plus h squared times 9 parentheses x plus h. So like this. So this red part represents f of x plus h. Then for f of x part, I just need to insert this x squared plus 9x. But remember, we must put parentheses around because we're subtracting this entire thing. Okay. Now we need to simplify. So we need to be able to simplify. So let's put different colors to show the simplifying step for each part. So for blue, we multiply these out. Then we get x squared plus 2xh plus h squared. For green part, we distribute 9. We get 9x plus 9h. For here, we have to distribute negative sign. That's how we get minus x squared minus 9x. Now we collect like terms. You see that x squared cancels out. 9x and 9x cancels out. So we have left with 2xh plus h squared plus 9h. So here h cannot equal 0 because if h is 0, right, there's no finding average rate of change between 2 points. Okay, so what we do is we can simplify furthermore. I'm going to factor h out from the numerator. Then I get h times parenthesis 2x plus h plus 9 over h. Then h cancels out, and we have left with 2x plus h plus 9. So what does this represent? This expression represents average rate of change of a function f of x equals x squared plus 9x between 2 points, x and x plus h. So using this, we can find average rate of change between any 2 points. So if x is 3, for example, and we want to find average rate of change between 3 and 7, then x will be 3, 3, and h will be 4. So I plug 3 and 4 here, it will tell us the average rate of change between 3 and 7. Okay, so this is more efficient calculating average rate of change between any 2 points. Okay. So now pause the video and try this problem. Which function below provides average rate of change for the function ft equals 3 minus 2 times square root of t on the input interval from t to t plus h. So essentially, which expression is a difference quotient which calculates average rate of change? Okay, so this is not simplifying. What's the first step when you put difference quotient? Okay, so try this problem. Again, when you try this problem, I suggest you actually write on your paper first. Do not look at the options here. Write down what you know first. Then try to find your answer in this multiple choice selection. Okay, so average rate of change is very important because this is one of the main idea that you directly see in calculus 1. So make sure you understand the idea of average of rate of change. And when we say average here, it is different from when we average our exam score or average height. It is different because average height, for example, is just one quantity, height. Average age is just one quantity, age. But because rate of change deals with two quantities, the way we compute average rate of change is different from when we find average age, average weight, average height. All those things are just one quantity. So don't focus on that, what you know about average. It is different because we're dealing with relations between two quantities and finding average of that.